All right, so let's do this. Today we're going to start in on our first new bit of of semester 2 material, chapter 14 on conjugated dienes. All right, to be clear, this week for homework, your homework revolves around that semester review, that first semester review. Your homework for this particular chapter won't be due until next week, but we're going to get started here. We'll talk about what this word conjugated means here in a second, but let's just pick apart the second word in this chapter here, dienes. First of all, diene. What does that E-N-E ending remind us of? Alkenes, absolutely. Compounds containing carbon-carbon double bonds. And then this prefix di, what do we think that corresponds to? 2, absolutely. So that is exactly what we're going to be talking about is alkenes, but specifically alkenes that contain 2 or more double bonds. Okay, so before we kind of dive in on dienes, what we're going to do is rewind and review things about alkenes that we discussed last semester, and then we'll kind of build off that with our new information, all right? So first of all, and this will be good review as well for your first semester review homework, we're going to start where we start with every new functional group, and that is on the nomenclature of these dienes. But again, first we're going to review just alkene nomenclature. So let's just pick an example, do something kind of easy here. All right, so we're going to do this example compound here. All right, step 1. I always am going to first find what? What do I look for in my molecule? The parent chain, absolutely, the longest continuous set of carbons. So first we're going to find what we call our parent chain. And absolutely that's our longest continuous set of carbons. Okay, but remember specifically when we started introducing our functional groups here, for example, our double bond, we're looking for the longest set of carbons with the one stipulation that it must contain that functional group, that it has to contain that double bond in there. So the longest continuous set of carbons containing our functional group. All right, so if we look here, my longest continuous set of carbons containing that double bond are these 1, 2, 3, 4, 5 carbons right here. Okay, now we have this one carbon sticking up here that is not a part of our parent chain. So the second thing we're going to do is we're going to find and name what we call substituents. That's anything that isn't a part of that parent chain. Again, it's this, in this case, this one carbon group right here. And what's that prefix for one carbon? Meth, and so this would be a methyl group right here. All right, now we got to number our parent chain. And when you start getting good at this, you can kind of just look at the molecule and see which way you should be numbering it. But remember, we kind of have this foolproof method where we can always go left to right or right to left, right? Number it both ways, and then we'll decide which one is correct. So 1, 2, 3, 4, 5. Or I can go the other way, 1, 2, 3, 4, 5. And the name of the game here is we want the lowest possible number in our name. Okay, so if I look, my double bond is between carbons 1 and 2, so we would label that with the locant 1. So that is the numbering scheme I'm going to pick, my red numbering scheme here. Right? And then the last step is to assemble the name. In this case, we're going to have to include that methyl group on carbon 4. So this would be 4-methyl. The double bond is located between carbons 1 and 2. Remember, we just always refer to it by the lower of the two numbers. So this would be 4-methyl-1-pentene. All right, so just like we sort of learned how to do, and we kind of rinse and repeat. Nomenclature the nice thing about nomenclature is we're going to do it every chapter, and our set of rules that we follow are going to be the same. We got to like add a new suffix in for each functional group that we learn, but in this case, we're just sort of reviewing here. So now I'm going to put down a few molecules, and you're going to take a second and name them for me. All right, so let's do this one. I'm going to find my longest continuous set of carbons. 1, 2, 3, 4, 5, 6. Now I have two substituents. I have this 2-carbon group right here. What do we call a 2-carbon group? So that prefix F. And then I have a 1-carbon group over here. We said that this would be a methyl group. And now we're going to number our parent chain in both directions. 1, 2, 3, 4, 5, 6. Going the other way. 1, 2, 3, 4, 5, 6. All right, let's see if we can remember here. Who thinks that we should pick the blue numbering scheme? And who thinks we should pick the red numbering scheme? Okay, awesome. So remember, when we have these functional groups have priority. I'm not going to pay attention to the methyl group or the ethyl group when I'm deciding my numbering scheme. I'm only going to focus on my functional group. I'm going to prioritize that functional group when I choose my numbering. So in this case, I'm going to choose the red numbering scheme because that's what gives my double bond the lowest possible number. All right, so we can just make a note here. When we number our parent chain, we're going to prioritize that functional group. Okay, and so now we have gotten ourselves to step 4 here, where we're going to assemble the name. Importantly, now that I have these two substituents, I have to order them in my name in a particular way. And how do we order them? Alphabetically, absolutely. So this would be 3-ethyl, 5-methyl, and then that double bond is between carbons 2 and 3, so 2-hexene. All right, for this one here, you just got to be careful. When we're finding our parent chain, it has to be the longest set of carbons, right? So even though it's tempting to say it's these 1, 2, 3, 4, because they're all in that zigzaggy line that we're used to seeing, our longest contiguous set is actually these 5 carbons here. I have a 1 carbon group we know is a methyl group. And I'm going to number my parent chain in such a way that prioritizes that double bond. So this would be 3-methyl, 1-pentene. All right, so this molecule here, finding my parent chain, 1, 2, 3, 4 carbons. Really doesn't matter which way we number it. Our double bond is always going to be between carbons 2 and 3. So this would be 2-butene. All right. But the problem is I'm not quite done here. You see, because I can draw another molecule that's really similar. This would also be 2-butene. But remember, double bonds, you cannot rotate about a double bond. So these are not just two identical molecules drawn differently. These are two distinct molecules. Remember, we have stereochemistry with our alkenes. So let's take a second to remind ourselves about our stereochemistry of alkenes. All right, and there is sort of cis and trans stereochemistry. That nomenclature works under a limited number of circumstances, but the universally sort of expanded nomenclature rules for alkenes are what are called EZ nomenclature, or EZ stereochemistry rather. Okay, so let's just review real quick how we go about assigning E or Z stereochemistry. Let me get rid of some of my markings here. Okay, because again, the whole point of nomenclature is to uniquely point to a molecule here. So we have to build into the name what the stereochemistry of our double bond is so we know which 2-butene we're talking about. Okay, so we'll just make some rules here. Assigning EZ stereochem. And step 1 is we're going to chop at that double bond. So I'm going to take my double bond here. Let me move this down. And I'm going to chop it in half. Hiya. All right, this first step is important because you don't just look at the molecule as a whole. You look on one side of the double bond, you assign priority. Then you jump to the other side and assign priority. All right, so we'll arbitrarily pick the left side first. So we're going to look left and assign high and low priority. All right, so what do I mean by that? If I look here at this carbon on this side of my double bond, it's an sp2 hybridized carbon. Yes, it's double bonded to this carbon over here, but it's got 4 bonds, right? So that means it's bound to 2 other groups on the other side. In this case, we have a carbon down here on this methyl group. And what else is that carbon bound to? That implied hydrogen that's sticking up right here. Absolutely. Remember, we just know it's there. We fill it in our mind's eye. So I'm going to look at that carbon and that hydrogen, those 2 groups that are bound to that carbon, and I'm going to assign 1 high priority and 1 low priority. Remember, the higher the atomic number, the higher the priority. All right, so then which one is high priority, the carbon or the hydrogen? Carbon. So this one is my high priority group. This one is my low priority group. Okay, so I did that for the left side. Now I'm going to do the exact same thing, but I'm going to jump to the other side of my double bond. I'm going to look on the right side. So step 3, we're going to look right and assign high or low priority. Similarly, we have a carbon up here and an implied hydrogen pointed down. Again, hydrogen being the lower atomic number, that's my low priority group. Carbon's got the higher atomic number, so this is my high priority group. Okay, and based on where those 2 high priority groups are pointed, we can determine the E or Z stereochemistry of our molecule, right? So step 4 is to assign E or Z. Okay, if we're going to assign Z stereochemistry here, that means that our high priority groups are pointed where? What is that stupid thing that we remember that's going to help us sink into our head? Z-zame-zide. If it's if it's a Z stereochemistry, that means that those 2 high priority groups are on Z-zame-zide of that double bond. So Z high priority on Z-zame-zide. And E is then the opposite if my high priority groups are pointed on opposite sides. So then my first example here, 1 high priority group was pointed down, the other one's pointed up, so they are not on Z-zame-zide. This would be my E stereochemistry. And to be clear, the stereochemistry goes in parentheses out front, followed by a dash. Okay, here in my other 2-butene, it's stereoisomer. My 2 high priority groups are pointed on Z-zame-zide. And so this would be my Z stereoisomer. We're going to do one example where you guys are going to assign stereochemistry, but real quick, let's go back to this first example here. Let me get rid of some of these markings so we can see a little bit more clearly. I didn't assign any E or Z stereochemistry here, okay? So if I'm being good, I want you guys to take a second and go back and tell me what this one should have been. So let's actually do this together here because we actually got a little bit of a tricky situation. Let's cut here. And let's actually look on the right first, because that's going to be the easy part, right? We have a carbon up here that's high, Down here is my implied hydrogen, that's low. If we jump to the other side though, we have a tie. These are both bound to carbons. All right, so remember what we do in the case of a tie is we're gonna list everything that those atoms are bound to. So in this case, this carbon is bound to one other carbon and 2 hydrogens, but this one's also bound to one other carbon and 2 hydrogens. So then what do? We just keep jumping down the line, right? So now I'm gonna go on to the next one. We're tied again, we have 2 carbons. So now let's list what they're bound to. Well, this carbon is a terminal carbon, so it's bound to 3 hydrogens. This one is bound to 2 carbons and a hydrogen, so this would be my high priority group, right? My carbons beat my hydrogens. So this is high, this one's low, and so absolutely my 2 high priority groups are pointed on opposite sides. This would be my E stereochemistry. And what about this example here? E or Z? Neither. How can we tell? How can we tell whether or not a molecule alkene has stereochemistry? It's bounded to 2 hydrogens, bonded to 2 identical groups, right? So let's say that we didn't know and we went and tried to play this game and we split at this double bond and then we looked over here to the left. Well, this is a hydrogen and this is a hydrogen. How the heck am I going to assign high or low priority? They're identical, right? So in any case where either of your 2 sp2 hybridized carbons are bound to the same group, you don't have any stereochemistry. There is no stereoisomer of this molecule here, so I wouldn't put anything out front here. This one is just 3-methyl-1-pentene. All right, so then let's just do one more. I want you all to do it on your own here. All right, so let's find our parent chain. That would be these 1, 2, 3, 4, 5, 6, 7 carbons here. If we number this direction, 1, 2, 3, 4, 5, 6, 7. If we go the other direction, 4, 5, 6, 7. So which numbering scheme are we going to pick, red or blue? Blue. We want our double bond to have the lowest possible number. So that would be that 3 position. We got this 1 carbon group right here, which we call a methyl group. So ignoring stereochemistry for the second and assembling our name, this would be 3-methyl, 3-heptene. Hept is that prefix for 7. Okay, so now let's zoom in here. Get rid of some of this so it doesn't get too crazy. I'm going to cut at my double bond. Let's look to the right first. It's a little bit easier. What do we think is high priority? This big old 3-carbon group down here, or this hydrogen? The carbon, yeah. So this one's high. This one down here is low. Over here, again, we have a tie. 2 carbons. So we're going to list everything that those are bound to. The carbon up top is bound to a carbon and 2 hydrogens, whereas this one down here is just 3 hydrogens. So that makes this my high priority and this my low priority. Those 2 high priority groups are on Z-same side, so this would be the Z stereochemistry. Cool. All right, so hopefully just review of alkene nomenclature, which was covered in the first semester. Now let's kind of complicate things a little bit by talking about dienes. And this is really just not very different at all. Nothing too crazy complicated here. There is just the smallest of twists that I'm going to throw at you. So actually, I think the easiest way to show this is just by analogy here. So let's put down 2 very similar molecules. One of them is just a normal old alkene, and the other one is a diene. All right, so this first one, my parent chain is 4 carbons long. That double bond is between carbons 1 and 2. So this would be 1 butene. All right, for our diene, we're going to do the exact same thing. We're going to find our parent chain, the longest continuous set of carbons that contains that double bond. We're going to find any substituents. In this case, it doesn't have any because we chose a relatively simple molecule. We're going to number our parent chain. And now we have to specify the location of both of those double bonds, right? So one of them is between carbons 1 and 2, so that's 1. The other one between carbons 3 and 4, so that's 3. So 1,3-bute, okay? Here's the weird thing. This is a diene, so we're going to put diene in the name. Not just 1,3 butene, but 1,3-butadiene, okay? But in organic chemistry, and we see this a lot, we'll see this in a few different times where we have these suffixes that start with not vowels, sorry, what's the other thing? Consonants here, all right? We never run 2 consonants together. Butadiene, right? It just like doesn't really roll off the tongue. So what we're going to do is we're going to retain that A from our butane. This is butadiene, all right? So you keep this A in here. This is the one little oddball about naming our dienes. We want to avoid running these 2 consonants together, so we're going to stick a vowel in between them so it sounds normal. All right, so 1,3-butadiene is how we would name this molecule. All right, so I'm going to put down 2 more. Let's see if we got it here. You guys take this on your own. All right, I'm going to give you a little hint here. This first one here, do these double bonds have stereochemistry? No, right? Both of them have two identical groups. Over here, though, they do, all right? So assign the stereochemistry here for those double bonds, and I'll show you how we build that into the name. All right, so this first one, I have that methyl group on carbon 3, so 3-methyl. My double bonds are located at 1 and 4. So this would be 3-methyl, 1,4-pentadiene. All right, the only trick, keep the A on the end of the prefix, okay? All right, for this one here, again, the complication is we have some stereochemistry. This first double bond is what, E or Z? So this one's E. What about my second double bond? Z, okay? So if I'm gonna name this thing without my nomenclature, without my stereochemistry, this would be 2,4-octadiene, right? Without my stereochemistry, 1, 2, 3, 4, 5, 6, 7, 8, yep, octadiene. So then how do I include my stereochemistry in the name? I again need to put them out front, but because we have these two different stereochemistries, not only am I going to put the E, I'm going to indicate which carbon has the E stereochemistry. So 2E, 4Z, then close those parentheses, 2,4-octadiene. Okay, so if you have more than one double bond with stereochemistry, you're going to have to put the locant in front of that E or Z designation as well. If you have a diene where one double bond has stereochemistry and the other one doesn't, you don't have to include the number, but including the number is never wrong. Okay, so you can always throw that number in there and it will be accepted. Both of them are entered into the database. But if you have both of them with stereochemistry, then you definitely have to tell me which one's which. All right? Cool. All right, so now moving on. Again, let's go back and review another aspect of alkenes that we discussed, and that was alkene stability. Okay, I'm going to put down 3 alkenes here, and I want you to see if you can't rank these from the least to the most stable. All right, if I label these A, B, and C, which one of these is the least stable up here? Does anybody remember the distinguishing factor? Say it again. That is, in terms of like our E and Z, that'll make a difference, but no, the big difference here is what we would call the degree of substitution. So let me show you what I mean by that. What we're going to do is we're going to look at our alkene, and specifically we're going to focus on these sp2 hybridized carbons. And we're going to count how many carbon neighbors they have. This one right here has 1, 2, 3, 4. This would be a tetra substituted alkene. What about this one? Mono, di, tri, tetra. What do we think? Everybody take a second. See if you can't decide. We're going to identify our sp2 hybridized carbons, and we're going to count how many carbons are they bound to. 1, 2, 3. So this would be a tri-substituted alkene. And then lastly, C. This would be a 1, 2, a di-substituted alkene. The higher the degree of substitution, the more stable the alkene. So A is the most, C is the least. All right, so substitution here is our distinguishing factor. This is what we learned in semester 1. The more substituted implies the more stable. All right, now, Bo makes a good point. There is, if I take these two let's say that I took two di-substituted alkenes here, this one, and then it's stereoisomer. Whoops, not that. This one down here. This one is more stable because those big groups are pointed on opposite sides. But it turns out that an even more important factor, and even like higher in the hierarchy of things here, is the degree of substitution. So what we learned about is our elimination reactions. They always favor these more substituted alkenes because those are the more stable. Okay, so we're going to kind of build off of this knowledge here talking about our dienes. But before we can really talk about stability of dienes, we got to talk about classification of dienes. So dienes we throw into different bins depending on just how far apart those two double bonds are from one another in our molecule. All right, so let's put a hold on this and take a second and talk about diene classification. Okay. And again, depending on how far apart those two double bonds are, we're going to throw them in different bins. So those two double bonds can be butted up right next to one another, right? So one side of my carbon has one double bond. The other side, that's where my second double bond is. This is what we would call a cumulated diene. Our double bonds are directly adjacent. we could have our double bonds with one single bond between them. All right, so now I'm moving my second double bond over one. These are what we call conjugated dienes. So this is when our double bonds have exactly one single bond separating them. Any further away, if I move this any further away than just one single bond, so now I'm going to move it all the way to the end here. This is what we would call an isolated diene. Okay, in this case, there are two single bonds. It doesn't matter how many there are between them. If there's more than one of them, we would call it an isolated diene, right? So our double bonds have more than one. Single bond separating. Does anybody remember what the name of the chapter is? Not just dienes, but conjugated dienes, all right? So this class in the middle here is really going to be the heavy focus of this chapter. When we start talking about reactions, we're really going to focus on that middle category here, okay? But first, let's just talk about classification. Again, depending on how far apart those dienes are, they fall into one of these three bins. Okay, and yes, the name of the chapter is these conjugated dienes. So these are kind of special. All right, so let's think about why that might be for a second. Let's take a look at a regular old alkene, just a double bond. We're going to kind of zoom in here. All right, and remember our double bonds, these two bonds are not identical to one another, right? A double bond is not just the same as having two single bonds in there. One of these bonds we would call a sigma bond, and the other one we call a pi bond. And the pi bond is really what makes an alkene so special. Remember we talked about alkanes, they only have the sigma bonds, and they're really boring. There aren't really any reactions involved in alkanes. And then we graduated to alkenes, and all of a sudden it was like, oh man, we got a butt ton of reactions to learn about alkenes. They're highly reactive. Why? Because they have these special pi bonds here. Okay, so why does that make them special? Well, remember, if we were to kind of like look at the electron clouds here, these two types of bonds look very, very different. A sigma bond, first of all, a covalent bond is made up of shared electrons, absolutely. So a sigma bond is kind of exactly what you would expect. Those electrons are being shared between those two atoms that are bound together, right? I'm bound to my neighbor over here. We're sharing a pair of electrons that's located directly between us. Cool, that makes perfect sense. The pi bonds are really weird. Not what anybody would have expected until quantum mechanics came along and explained what the heck was going on here. But those cloud of electrons are no longer sitting between those two carbon atoms. They're sitting in clouds above and below the plane of that bond, right? It's the sharing of electrons above and below that sigma bond. And that cloud of electrons is much more easily accessible, which is what makes these alkenes more reactive. Okay? Remember, these carbons in my alkene are sp2 hybridized. That's because they got this leftover p orbital here that can participate in this pi bonding. Okay? So now let's go back to our conjugated diene here. All right, what's going to be the hybridization of this first carbon? sp2, right? Just a normal old sp2. What about this one? Also sp2. What about this one? Also sp2. What about this one? Also sp2. So what makes our conjugated dienes so special is we have sp2 hybridized carbons all lined up next to each other, all in a row here. And remember, each one of them has this cloud of electrons, this little peanut-shaped cloud that's participating in this pi bonding. But because these electrons are all lined up next to each other, they're sitting above and below the plane of these atoms, all in a nice row here. What happens is these electrons, they're not going to stay put. They're going to spread themselves out to all possible positions. So these two bonds right here are going to be connected by those electrons delocalizing, spreading themselves out. What do we call it when electrons spread themselves out? The R word. Resonance, absolutely. And so these conjugated dienes here, they have these resonance structures that are available where these electrons can spread themselves out. And what do we know about resonance and energy? Is resonance a stabilizing effect or a destabilizing effect? Stabilizing, absolutely. And so what we're going to see is these conjugated dienes are very, very stable because these electrons are all lined up in a row, or rather these orbitals are all lined up in a row, allowing those electrons to delocalize across them, providing this stabilization effect. If we go to our isolated dienes, and we can just think of this name, isolated, what does that mean? Well, if we play the same game, these are sp2 hybridized, these ones are sp2 hybridized, but sitting right in the middle here is what? An sp3. So we got something right in the middle here that blocks any sort of connectivity between those two orbitals, right? These two double bonds can no longer talk to each other. They got this sp3 carbon in the middle, F'ing everything up. Okay, so there's no resonance that would be available to those isolated. Again, hence the name isolated. They're sitting there far apart from one another. They can no longer talk to one another. So then the weirdest one is the cumulated. And it's very natural to say, man, these are sitting right next to each other. Can't they talk to one another? And the answer is actually no. Okay, and this is a little bit tricky to see. On the end, this carbon is sp2 hybridized, so it's got its pair of electrons. But this carbon in the middle is not sp2 hybridized. It's only got two bonding regions. One double bond on one side, one double bond on the other side. So this one would just be sp. That means it's got one peanut-shaped orbital sticking up in one direction, but the other one is exactly perpendicular. So these electron clouds are no longer lined up next to each other. They're in different orientations, and the electrons cannot spread themselves out between it. All right, so yes, we have these two pi bonds, but one's located up and down, the other one's located left to right. Those pair of electrons cannot spread themselves out. In fact, what we see in terms of ranking our energy here, cumulated is the worst, meaning the least stable. So cumulated is the least stable, whereas conjugated, we said because of resonance, these are the most stable. And isolated is then in between. We can call this mid-stable. Okay, so We talked about last semester one big factor affecting alkene stability, the degree of substitution. Now that we're talking about dienes, we're going to throw this other bit into the mix here, this classification, how far apart those double bonds are. All right? So what we need to be able to do is if I put down a few molecules, you're going to rank them from least to most stable. All right? So now we're going to talk about stability of dienes. The most important factor is that one that we just discussed, that classification. The second most important factor is that degree of substitution. And then lastly would be the stereochemistry, the idea that we want big groups pointed on opposite sides, right? But if I'm sort of going to rank these factors here, classification is the most important, then we go to substitution, then finally stereochemistry. All right, so I'm going to put down 4 molecules, and you're going to tell me, you're going to rank them, least to most. All right, so since the most important factor here is the classification, let's go through and classify these dienes here. What class would this first one go in? These are our conjugated. All right, and again, I can see I got this line of sp2 hybridized carbons all in a row here. All right, that's the key. What about this next one? These ones are isolated. I got this sp3 hybridized one in the middle here, messing everything up. preventing those two from communicating with one another. So this is isolated. What about my third one? This one's also conjugated. And then the last one, accumulated. Okay, and let me just real quick so that it's normal when you see it. Your homework does not put, I like putting the C there, I just feel like it makes it easy to see. Your homework system actually just leaves it as one like unnaturally long double bond with the tiniest little space between them there. But they're pretty easy to see because it's like, why the heck is that double bond so freaking long? All right, yes, but anyway, your homework system doesn't actually explicitly write the carbon in between them, it just kind of leaves it looking like this. Okay, cool. So right off the bat, let's just say A, B, C, D. I know which one is going to be the least stable. That cumulated, right? Cumulated's bad. Followed by B. Okay, so A and C, though, are both conjugated. How am I going to distinguish between which one of these two is more stable? Now we got to go to the next factor here, that degree of substitution. All right, so if we look here, what's the degree of substitution on this one? Mono, di, tri, tetra. This one's just mono, and this one's di. But in C, both of them are di-substituted, right? So yes, both A and C are example of conjugated dienes, but C just has a higher degree of substitution, right? So that's how we can tell that the next will be A followed by C. And again, these are ranked from least to most stable. All right, cool. So what we're going to do next is kind of start in on some reactions here. We're not going to really be able to finish this, but I just want to sort of introduce, and again, we're going to start back where what we should know, which is just talking about alkenes, and then we'll extend that concept to our dienes. Okay, so reactions of alkenes. All right, so first of all, let's remember that our reactions of alkenes, 99.9% of them fell into one particular class of reactions. Does anybody remember what that is? Not substitution, not elimination. What did alkenes do? Addition. Yes, addition reactions. Awesome. And we're going to see the same thing for our dienes as well. So these are going to be addition reactions. All right, so what do we mean by that? Well, if we just take a normal old alkene and we're going to do a hydrohalogenation reaction, these things aren't going anywhere, they're coming back. What we see is to one side of that double bond, the hydrogen gets added, and to the other side of the double bond, the bromine gets added. Right? So these addition reactions. And what we learned about these reactions is you can't just put the bromine anywhere you want. It's going to go on one specific carbon, the more substituted of the two carbons. Okay? And that is because in our mechanism here, if I'm going to be good and draw my reaction mechanism, there is a carbocation intermediate. Just for the sake of practice, take a second and finish off this mechanism for me by drawing in the missing electron pushing arrows. right, so the last step here, we have one bond formation arrow that we need to draw. Okay? But the reason that we have this, what we call regiospecificity, this Markovnikov reaction, is because the carbocation wants to form on the more substituted carbon. All right, so we had this whole logic here that revolved around carbocation stability. Where the more substituted, the better, right? So if we have a carbon that has 3 hydrogens, this is what we would call a methyl carbocation. You're never going to see a methyl carbocation. These are the least stable. Followed by primary, then secondary, and then finally the most stable, a tertiary carbocation. All right, so let's remember when we discussed these addition reactions with our alkenes, our regular alkenes, we had to put that bromine in a specific place, what we called the regiospecificity of these reactions. And that arose from the stability of that carbocation intermediate. And we said that the more substituted that carbocation intermediate, the more stable, right? So the bromine will always go on the more substituted carbon. Cool. All right. So now let's take this concept and kind of extend it to our dienes. All right. So now we're going to take something very, very similar here. But instead of just looking at a normal old alkene, we're going to look at a diene, specifically a conjugated diene. Because again, that's the title of the chapter. We're again going to react it with HBr. And the first step in this mechanism is going to look the exact same with what we saw above. Just like alkenes, the reactivity of conjugated dienes comes from that pi bond. So that pi bond is going to play the role of a nucleophile and attack that acidic hydrogen, breaking that bond right here. All right, but again, we have two different options for what our intermediate looks like. Right? Either the hydrogen is going to join here, putting my carbocation here, or I'll get the reverse. My hydrogen joins up here, and my carbocation down here. Okay. Now, in terms of what we just discussed, primary, secondary, tertiary, both of these are what? Both of these are secondary carbocations. So given what we just discussed, I'm not going to be able to distinguish whether one's more stable than the other, okay? But now we have that other double bond there. So looking carefully, let's see. Let's take a vote here. Who thinks that the blue one would be the more stable carbocation? And who thinks the red one would be the more stable? Why the blue?
It can participate in resonance with...
Boom! Magic R word again. Absolutely. Can participate in resonance with that nearby double bond. And so absolutely, this is not going to be the carbocation that forms. The carbocation is going to form in what we call the allylic position. Remember those allylic carbocations, right? So absolutely, we're going to get the allylic carbocation. And if we go ahead and scroll back up and update our stability chart here, you want to know what's even better than a tertiary carbocation? A resonance stabilized carbocation, right? So even more stable would be that allylic position carbocation. Right? Remember, allylic means that it's one next door to that double bond. So just to finish this off here again, we have our allylic carbocation. We're not going to take this red path at all. So my product of this reaction here will now have that bromine in that allylic position. All right, and we're going to call it here. This isn't actually the full story for these particular type of reactions. There's a little bit of complication we're going to throw in here, but this is a good stopping point. This concept of resonance is going to be extremely important in that chapter, right? That's the whole idea behind the spacing of those two double bonds in a conjugated diene. And actually next chapter, as the next 3 chapters, resonance is going to feature kind of heavily in. Okay, so we're going to sort of complicate things a little bit here next class, and it's going to very much so have to do with the resonance structures that are available to that allylic carbocation, but we'll sort of end it there because that's a good stopping point. Cool.